Okay, so to start today's lecture, I need a volunteer. Tut. Sadece oradan. Sadece oradan. Bir dakika. So, okay, now he's holding the wheel. Can everybody see the wheel? He's holding the wheel. I am holding the wheel. So what do you think it will happen when I leave my hand? It falls. Now let's rotate it. Anybody who wants to try, who doesn't trust us, that we might be doing some tricks? So would you like to hold it? Okay, so she is holding it. She will not rotate the wheel. I will first rotate the wheel and let it go. So anybody else who doesn't believe it? Who wants to try? So now everybody trusts us? Okay, so this is where we are heading to. Why does it do that? This is what we will be able to study probably in next week or the beginning of the following week. And this is not a special wheel, by the way. This is just my bicycle's wheel. So you can look at it. There's no trick in the wheel either. Okay. Now let us see what we have done. So does anybody want to record it to a video? We can repeat it if you like. Okay. Well, the video is over there anyway if you want to see it in a few days. Okay, so we started studying rotational motion. We first started with the kinematics. And, well, let's look at the kinematics of this thing, by the way. We just looked at the wheel. Okay, the kinematics was, okay, we were rotating it. There was that rotation around this fixed axis. Okay, the wheel has this fixed axis. If I hold it and rotate it, this is the first simplest motion that we can imagine. Then to describe its state, we defined this angle theta. And the change in this theta we call the angular velocity. Okay, we had the angular velocity, which was a vector along the direction of the axis. And we used the right-hand rule to determine its direction. And then once we determined the angular velocity as a vector, the linear velocity of any point was nothing but the angular velocity vector cross product with the position of that point, the vector that denotes the position. Now, in this relation, you have to make sure that the origin, the axis of origin, you have to pick along the axis of rotation. The origin of your coordinate axis should be on the axis of rotation, and that is this r over here. Then the acceleration. The tangential acceleration, we can also write in terms of the angular acceleration alpha cross r. Now, if you imagine any point on this wheel, right, if it is rotating with constant angular velocity, then it has a central acceleration pointing in this direction. But the angular velocity might also be increasing, so it will have a tangential acceleration also. So it's only the tangential acceleration that is determined by the angular acceleration. Okay, so if you have a motion with constant angular acceleration, these are just like the linear translational motion case. And then we talked about the torque. I will not repeat these. Well, the torque was the last thing we did, I think. We didn't yet do the rotational kinetic energy. Okay, so by the way, that is the idea why I repeat what we did, at least in a few sentences at the beginning of the lecture. So if you have any questions, you should ask now. This one. Okay. The first pages. Yes. So what's your question? Oh, this one. I mean, you mean the formulas or this? Well, the angle theta. So how we define the angle theta? Any problem in that? No. Okay, so then we have, well, we define the alpha vector at the time t is kind of the derivative of the omega vector with respect to t. So this just tells me that the change in the omega vector is nothing but the angular acceleration at that time times the time interval at which that acceleration exists. So omega of t minus omega of 0, this is the change from the t equal to 0 to some final time t. Well, the total change is nothing but the sum of these changes. But some of those changes we just denote by an integral. Starting from 0 up to t. Well, we can, if you would like to. Well, let me first write it as a sum. Alpha of t dt. Now, for notationally, what we mean by sum is, okay, you have the first term plus the second term plus the third term plus the fifth term. Or in terms of times, you can just say that, okay, I start from t equal to 0 seconds to t equal to 5 seconds. I can have the 1, 2, 3, 4, okay. 1, 2, 3, 4, and this is the 5. T equal to 1, t equal to 2, 3, 4, 5. It might happen that from t equal to 0 to t equal to 1, it will have some constant acceleration. From t equal to 1 to 2, it will have some other constant acceleration, and so on and so forth. This might be the case. Then to calculate the total change, what we need to do is, let me just call this alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. Okay, the total change in the angular velocity would have been, this is alpha 1 times 1 second, plus alpha 2 times 1 second, plus alpha 3 times 1 second, plus alpha 4 times 1 second, plus alpha 5 times 1 second. And this I can also write as sum over alpha I times 1 second, I from 1 to 5. This is perfectly correct. But in general, this is not the angular acceleration as a function of time. In general, what we would have is this one. So this is 1, 2, 3, 4, 5 seconds. So it would just go like this. This will be our acceleration. This is not something like steps like this one. What I can still do is I can just divide this into very small intervals, very small ones. Now, of course, the time interval will not be 1 second anymore. It will be, let's just assume for simplicity that the time intervals here are just the same. They're all dt. Now, I can say that, okay, within this time interval, the first one, This is the time interval 1, 2, 3, 4, 5, 6, 15. I don't know how many time intervals I have, or 25, let's say. In this, the length of this time interval is, well, dt is just 5 seconds divided by, I don't know how many intervals I have, let's just call them n. Now, the acceleration at this step, do I have a color? Yes. Now, the angular acceleration in this step, t equal to 0 to dt, it changes with time. But I can still approximately just assume that it has a constant acceleration here, angular acceleration there. This is just an approximation. Of course, I will be introducing some errors. But the smaller this time interval is, the smaller will be my errors. But for a first approximation, I can just take it to be constant. This is constant. Here it is constant. Here it will be constant. Here is, I will assume, constant. Another constant. Constant. So now it is step-like. Now this is the first interval. Or if I look at the fourth interval, this is, well, the time here at this point is 3 dt. So the acceleration at the fourth interval, alpha 4, let's call it, it is nothing but alpha 3, alpha at the time 4 minus 1 dt. Of this broken curve. Now, this broken curve, if I just, okay, so this is the alpha 4, the time interval, the change in the, my velocity, okay, this I'm at the fourth interval, so it is the 1, 2, 3, 4, omega of 4 dt minus omega 3 dt. This is the change in the velocity as I go from 3 dt to 4 dt. This is equal to alpha 4 times dt. It is the change in the angular velocity in this time interval is just alpha 4, the angular acceleration at this time interval, multiplied by the time, because I'm just assuming that angular acceleration is constant. It is almost constant since I'm taking a very small time interval. It doesn't really change much in that time interval. Now, so if I want to calculate the alpha n dt, no, omega n dt minus omega 0, I just need to sum all these changes. This is equal to alpha I dt. I going from 0 up to n minus 1. So I start from t equal to 0. This is alpha 0, alpha 1, alpha 2, alpha 3, up to alpha n minus 1. So this is what I should write. This is equal to I is equal to 0 up to n minus 1. Alpha, well, alpha I will be just like this. The constant acceleration, I assume that the ith interval is the, in fact, the acceleration at the time I dt minus 1. Now, I minus 1 dt. This is what my broken curve does. This is quite valid. This is just an approximate number, though. If I want to get a more precise value, what I should do is I should just, because that would give me the change in the angular velocity if my acceleration as a function of time was given by this broken curve. Now, this broken curve is almost like my original curve, but not exactly. So this is my broken curve. Now, if I make these steps smaller and smaller, then my broken curve will become more close to my real curve. You see, this is a phenomenon, in fact, that you see every day whenever you watch TV. Do you remember the times when there was no high-def HD TVs? Okay, so you are still old enough to remember those old days. Okay, so in the old days, you could see that the pixels were just quite rough. If you looked at the TV from a very close distance, when you look at an image from a far distance, you would see such a shape. But from a very close distance, you would see that this is, in fact, such a line. It is not a straight. It's not really a curve. Now, the only thing that has changed is that these steps are much smaller in HD TV, high-definition TVs. Yeah, that's the definition of high definition. So these steps are more closer, so they are more similar to a curve. They are still not a curve. It's still steps, but you cannot distinguish the two if you don't look with a magnifying glass. The same thing here. If I take these steps closer and smaller, if I make a high definition representation of this smooth curve, I will get a more precise value. But taking these steps smaller means that I have to take this dt, the step size, to very small numbers. But remember, my step size is determined by the number n. If I have smaller steps, I need to take more steps. So as I'm taking this dt to 0, I have to take n to infinity. I have infinitely many steps between t equal to 0 to t equal to 5. And of course, keeping this number n minus 1 dt is equal to 5 seconds in our example. That's our total time interval. Well, this is the difference, the change in the angular velocity between time t equal to 0 to and 5 seconds. This is exact. In this limit, this will be exact. Well, rather than writing this sum and these limits all the time, we just invent a different notation for this limit. Rather than showing all these things, we just say that, okay, this is, oh, by the way, I have to multiply this by dt. It is this dt over 2. So rather than writing this limit and this summation sign, we just write it as sum of alpha t dt, t starting from 0 to 5 seconds. Rather than using the Greek letter sigma, we use the Latin letter s for sum. We just stretch it a bit. You just hold it from the ends, stretch it a bit, so it just becomes what you know as the integral sign. That is an s, by the way. So that integral is nothing but the sums of the differences, and that is what we write over there. So the change in the angular velocity from time 0 to time t is nothing but that sum from 0 to t of alpha dt. And this, if we know the angular velocity times time is the change in the angle theta. So the change in the angle theta from t equal to 0 up to time t is equal to t is just that sum from t equal to 0 of t of omega dt. Yes? Why? I didn't understand the question. Okay, I still didn't understand the question. Okay, any other questions on this? Okay, so we defined the torque. This is where we left. We defined the torque acting on an object. We calculated the total torque, and at the end, now we also did an example of the thin rod, but we will come to that thin rod example later on. We had this, we defined this moment of inertia thing. And then we looked at the moment of inertia of a thin rod of length L. Okay, so let's go back to our wheel. It's rotating. Well, since it's rotating, by the way, can somebody, who wants to try one more thing in this rod? I need some volunteers. Okay, you come, you also come. I have to. Your hands will get dirty this time. Your hands will get dirty. No, because, okay. Hold it from here. Hold it tight. No, you don't. You will try it later on. Now, what I'm asking you to do is I will rotate it, let it go, and I want you to take this thing and turn it around. I want you to do, yes. I want you to do that motion while it's turning around. And describe the class what you feel. Why did you take it up? Huh? Yeah, well, you did. You were holding it.
Yes, but it made me do this.
Okay, so he didn't do it. That is his claim.
Yeah,
Okay, so, okay, I don't believe him. So let's try with her. Will you be able to hold it? Hold it tight. So I want you to move it horizontally. And not like him, don't lift it up. Why are you rotating it? Okay, this was another interesting thing. We will describe it. I mean, if you want to try it, you can try it in the break. Okay. Now this thing is rotating. You have the masses at the edge. They are moving. They are point masses. But we already studied point masses. So when the point masses are moving, they have kinetic energy. So this thing, if it's rotating, it should have some kinetic energy, because each part is having kinetic energy. So we can just sum the kinetic energies of the parts and obtain the total kinetic energy of my system. We will need kinetic energy because we would like to discuss conservation of energy eventually. So we have our rigid object. Just imagine that it's a three-dimensional object. It is rotating around this axis. So let's say that this point, which is at a distance r from my axis, is moving in this direction with some speed v. I can just imagine that there is well, I'm just dividing all my mass into very small point masses. Mi. Then the kinetic energy of this single point mass will be 1/2, well, let's call it the Vi. 1/2 mi Vi squared. This is the kinetic energy of that point mass. Now, if I divide all my mass into these very small segments and sum them all up, sum over all my different masses, this will be the total kinetic energy of my system. Well, if you like, we can even convert this into an integral. The mass will be just rho times the volume. V at the point r squared 1/2. If you want to play with integrals, just try to see how you can relate that sum to such an integral. This is for you to play with. Let's stick with this one. Now, the speed of this object, if my object is rotating with angular velocity omega, this is the perpendicular distance of this point from my axis, then the speed, let me just call it Ri to denote the distance of the mass mi from the axis of rotation. Its speed will be just Ri times omega. omega is the angular velocity of my rigid object as a whole. It's not the angular velocity of that point. It's a property of my object as a whole. So if you just plug it over here, 1 over 2 mi ri squared times omega squared. This is equal to 1 over 2 I mi ri squared times omega squared. This thing you should remember already from the previous lectures. We had defined this quantity that we will see quite often in rotational motion as the moment of inertia of my object. So this is 1 over 2 I omega squared. This is the kinetic energy of rotation for my object. This you can imagine as a kind of an internal energy of the system. You see, if you remember when we were discussing collisions, now the momentum is conserved in collisions, but if you just imagine that you have a mass m moving with velocity v, then you have another mass, let's say equal mass m, and moving with the same velocity in the opposite direction. And if you just imagine that when they come together, they collide and they stick together. If they stick together, just conserving linear momentum tells us that after the collision, the system is just at rest. So the question is, what happens to its kinetic energy? And when we were discussing the the kinetic energy and the conservation of energy, we said that whenever there seems to be an energy violation, the lost energy is usually converted into internal energy of the system. Okay, my center of mass is at rest. The system as a whole doesn't move in this case. But what will happen is my system will start rotating around its axis. So for this, if they collide and stick together, they will just start rotating. And since they will be rotating, they will have some kinetic energy for rotations. And that is where the initial energy will go. Of course, assuming that these masses, they do not get deformed. So each one of these have their internal energy. Assuming that that internal energy doesn't change in this collision, the energy of this collision of the system will be converted into rotational kinetic energy. And that is what we obtain over here. The rotational kinetic energy is 1 over 2 I omega squared. Well, up to now, we have been studying only systems with fixed translational, fixed rotation axis. Now we will add one more ingredient to it. If you are riding a bike, for example, take this bike, this wheel, you don't hold the axis and rotate it like that. What you do is you just take it, ride it, the wheel rotates, and hopefully you will be covering some distance. So you have both translational motion and rotational motion. Now usually what we will see is, this is a complicated motion, but the motion simplifies a lot if you just consider the motion of the center of mass plus the motion relative to the center of mass. Now if you take this example, I have my wheel. My wheel is, let's say it's rotating. It can be any object. If you just throw this chalk, it will be doing some translational motion and rotational motion at the same time. So you have your rigid body. It has some angular velocity, omega. It is also if this is the center of mass will also have some velocity v. Now we can, okay, whenever we have such a system, first you have to choose some fixed coordinate axis. You have to specify your reference frame. So I will just assume that I have some inertial reference frame somewhere, and this is the origin of my coordinate axis in that inertial reference frame. This is completely arbitrary. Then the position of this mass of the center of mass, I will denote by the r center of mass. I will just repeat the previous definition. The only derivation here, the only difference will be I will just assume that the center of mass is also moving. So I have the position of the center of mass, plus if you just imagine one small mass over here, the position of that small mass, mi, will be given by ri. So this is what I have. Now the total kinetic energy of my whole system. Okay, so let me also denote the position of this mass mi relative to my fixed reference frame as ri, the capital Ri vector. So I have the small r denotes the position of my mass relative to the center of mass, and the capital R is the position of my this infinitesimal mass relative to my original coordinate axis. What do I know? That the Ri is nothing but our center of mass plus the small ri, because I can just go from this origin to my point straight, or I can just first take this vector and then take this vector. I reach the same point. So those two vectors have to be the same. But this means that the velocity of my ith point relative to the fixed coordinate axis is equal to the velocity of the center of mass plus the velocity of that small mass relative to the center of mass. So you can just imagine that somebody is riding the bike. So the wheel is turning around, rotating. I look at the wheel. There is this point. Let me just pick this reference point. The center of the mass is moving relative to me, but this point is also moving relative to the center of mass. So the velocity of that point relative to me will be the velocity of the center of mass plus the velocity of this point relative to the center of mass. So it will be the sum of those two velocities, and that is what we are writing over there. Now I can just write down the kinetic energy of the system. Now the kinetic energy of the system, 1/2, the mass of that system is mi. Okay, question. I saw some right-hand rule applications over there. The bicycle. We wait for 10 days or almost. It is the same problem. In fact, I mean, when your friends try to hold this without rotating it, they had some difficulty. The reason why it is rotating when you are holding it like this or with this string, and the reason why it is stable if it's moving, is the same thing. They have the same reason, but we need to study the angular momentum before doing that. First, let's just stick with ignore the angular momentum for the time being, and then we will come to it next week. Okay, 1/2 mi vi squared. This is the sum of the kinetic energies of each individual parts. This is equal to 1/2 mi v center of mass plus the velocity relative to the center of mass, everything squared. Well, I'm just putting this in the definition of the total kinetic energy of the system. I will just take this square, 1/2 mi v center of mass squared plus 1/2 mi vi squared plus 1/2 mi v center of mass dot vi twice. And okay, so let's start with this one. This kind of looks nice. 1/2 is just a number. I can just take it out of the sum. This is just a fixed number. It doesn't change as I change my mass m. What remains is the sum over all the masses of my point objects, but that gives me the total mass of my system. This is just as if I have an extended object, we had already seen that in terms of translational motion, my extended object just behaves just like a point mass located at the center of mass if there are external, I mean, in terms of for the translational motion. I can just, if I'm just studying the translational motion, I can replace my mass as a point mass at the location of the center of mass and feeling the total external force acting on my system. So this is nice because this just tells me that this term at least is just as if all the mass is moving with the center of mass velocity. I'm just again replacing my extended object with a point mass located moving with the center of mass coordinate, and this will be its kinetic energy. Yeah, this term at least is kind of nice. I have this one. Well, this one doesn't really, well, this is the kinetic energy of my system relative to the center of mass. Because this velocity is the velocity relative to the center of mass, but that means this is the kinetic energy relative to the center of mass. But we had already calculated it. The kinetic energy relative to the center of mass is nothing but 1/2I omega squared. This is the internal energy of my system. The only complication is this one. Now, what to do with this one? Let's just look at it. This is, okay, V center of mass is a constant. These two, they cancel each other. So I have V center of mass, scalar product with the sum of Mi, Vi. So the first two terms are kind of nice. I have the translational motion of the center of mass, so there is a corresponding kinetic energy. My system is rotating around the center of mass, so there is a rotational kinetic energy. So this is what we could have guessed. So what will we do with this one? What does that sum correspond to? It is a sum that we had already seen. What is mass times the velocity? Momentum. So if I'm summing, this is the momentum of the ith mass. I'm summing over all of them. This is the total momentum of the system, right? With respect to which reference frame? With respect to the center of mass. So that means that, well, what is the velocity of the center of mass relative to the center of mass? So the momentum of the center of mass relative to the center of mass is also 0. That term is just 0. Yes? Well, if you take the square of the sum of two terms, a squared plus b squared plus twice ab. That term is 0. So that term is 0 because we decided at the beginning to write everything with respect to the center of mass. So only in that limit, if you have any object that is making both a rotational and a translational motion, if you describe the translational motion as a translation around the center of mass, then you have this simplification. The center of mass motion is just like the motion of a point mass, and the rotational motion is just kind of independent of the motion of the center of mass. Now the complication here is, if you take this object, so who wants to sacrifice their finger for science? Now I want you to put your finger around through this point. So he will really sacrifice his finger, by the way. I will rotate this wheel. So if I'm rotating my wheel, you can say that the wheel is rotating around this axis that I'm holding. So is the wheel rotating around your finger?
Yes.
So I can describe this system in two different ways. Well, infinitely many ways. I can just say that, okay, the wheel is rotating around this fixed axis that I'm holding with some angular velocity. Or I can say that the wheel is rotating around this center of this axis, but that axis is also having some translational motion. they will give me the same description. Thank you. They will be identical. They should be identical. Because the rotation, if you include the translational motion, the rotation axis is not unique. You can define any point, any axis as your rotation axis. But if you choose an arbitrary point for rotational axis, like this axis over here for such a rotation, then the resultant equations will be quite complicated. The simplest thing, just like whenever you are choosing some coordinate axis, you can choose any coordinate axis you like. In certain coordinate axes, the equations will look much simpler. Just like that one, in translational and rotational motion, if you choose the center of mass, if you choose an axis that goes through the center of mass, most of the time your equations will be much simpler. So you will have this splitting between the kinetic energies, the kinetic energy of translation of the center of mass plus the rotational energy around the center of mass. In any other axis, you will not have this simple picture. Yes? Well, you see, this the small r(I) is the position of my object relative to the center of mass. Okay? So this vi is nothing but dri by dt. That is the velocity of my object relative to the center of mass. Now, if you just consider this one, the wheel is rotating and it is slowly going in this direction. Okay, no, it is moving fast. Or even we can just put it here and it's rotating. In my reference frame, this point is fixed if it's not slipping. It has 0 speed relative to me. But if you go to a reference frame in which this point is fixed, if I start moving with this rotation axis, let's say, that point is moving in that direction. Okay? So whenever you are talking about the velocities, you should always specify according to which coordinate axis, and this vi is the velocity relative to the center of mass. That is how I define this ri. So this is the total momentum of my system. This is the velocity relative to the center of mass. This is the momentum of the ith mass relative to the center of mass. If I just sum over all the momentum, this is the total momentum of the system. But this we can write as the total mass times the velocity of the center of mass. This is how we define the velocity of the center of mass. But this velocity of the center of mass, let me put a prime. This velocity of the center of mass is, well, since its vi's are all relative to the center of mass, this is the velocity of the center of mass relative to the center of mass. But you are never in motion relative to yourself. So center of mass is always at rest relative to the center of mass. So this velocity is 0. So this sum has to be 0. Or you can imagine it like this. When you go to the center of mass of the system, if you have some momenta in this direction, you have some other momenta in the other direction, such that the sum is 0. That is how you define the center of mass, such that when you go to the center of mass, move with the center of mass. If some objects are moving in this direction, some other objects will be moving in the other direction. The sum will be 0. In this example, if I just move with the center of mass, which is right at the axis, this point is moving in this direction. This point is moving in the other direction. So if I just sum the momenta of this part and this part, I get 0. The same holds for this part and this part too. Any other questions? Okay, did you think about the hurricanes? Did you check the YouTube at least? Okay, so your homework for next Tuesday is to check the YouTube. Okay, we will discuss it next hour after the break. Okay, so this is my rigid body. It is rotating. Now, at this moment, all the points are, well, where is my reference point? Okay, this is my reference point, which is at rest, this point. Sure. Or let me do it like this. Let me just that point is at rest. Right? No, that point is at rest. Now, if I start the rotation of my wheel, that point starts to move. It has a finite speed. Initially, it had 0 speed. Now it has some finite speed. So, at least at some point between this time and this time, it should have some acceleration in this direction. That is tangent to tangent to the radius, tangent to this circle. So that's what we call tangential acceleration. Now, if it is rotating at constant speed, then it means it doesn't have any tangential acceleration, because it's moving at constant speed. The speed doesn't change. But still, it has some acceleration, but the acceleration is in the direction of the center. So it has a central acceleration if it's rotating with constant angular velocity. But if the angular velocity is accelerating, it also has a tangential acceleration because its speed is increasing. Okay. So now the angular velocity is pointing towards the class.
And center of mass
Is somewhere over here. Now, is it moving?
yes.
So if you just rotate it like this, it doesn't have, the center of mass is at rest. If we start moving it, okay, now the center of mass has some velocity in that direction.
And last lecture you showed me the angular velocity towards the class.
Okay.
And there is one more velocity towards this direction. It's just
Now, okay, so if it is rotating like this, let us hold it, put it back. Okay, so we are talking about two different velocities, the angular velocities and the linear velocity. Now, if you just rotate it like this, the center of mass doesn't have any linear velocity. The center of mass is at rest, relative to our reference frame, relative to the reference frame of the class. It has some angular velocity. Use the right-hand rule. Its angular velocity is pointing in this direction. If you take any point on my rigid body that is not at the center, that's not on the axis, it has some linear velocity. Now, if it's rotating like this, the points over here have linear velocity in that direction, the points over here have linear velocity in this direction. Now, if this point has velocity in this direction, tangent to the circle it is drawing, because all the points on the rigid body, this point has a velocity in this direction.
And what is the force or velocity in that direction?
Well, this point has velocity in that direction. And this point has velocity in this direction. Any other question? Okay. No, I don't want a Coriolis effect. We are in inertial reference frames, and there is no Coriolis effect in inertial reference frames. We are not discussing the hurricane problem now. We are giving a break now. If you have a question about the other things that we had done, we can discuss it before we give a break. And if you want to play with it, you are welcome to.